Hi everyone, I'm Felix. Today I'm going to share about our work, a formalism of DNN Accelerator Flexibility. DNN applications are everywhere. As the quote from Andrew says, AI is the new electricity. To run this DNN model with runtime and energy efficiency, people start to build specialized hardware for it, which we call DNN Accelerator. Now let's take a look at the template of a canonical DNN Accelerator. First, it will house hundreds of thousands of processing elements, and we will use what we call data flow or mapping to map the DNN computation onto it. So there are some higher order bit of the DNN component in the accelerator. First, we will have PE array. In each PE, there could be 1 to several ALU units. Second, we will have hierarchical buffer, for example, small local scratchpad beside PE, share global buffer, and off-chip DRAM. Then we'll have network chip NOC to distribute and reduce the data across the processing element. Then we'll have mapping. It tells how the DNN workload are mapped onto the accelerator. It could include like tiling, ordering, parallelism, and shape, and we will go into detail later. So for hardware design, we often specialize the control path and data path to tailor for one to few specific application or workload for energy efficiency. However, specialization is particularly challenging in DNN workload because there are huge diversity in DNN workload, and like there are different layer size, shape, and computation type, and also we have depth-wise, point-wise convolution, and also pruning make the workload have even more diversity. So all this diversity make like hardware support for DNN become more challenging. Therefore, state-of-the-art DNN accelerators start to add flexibility in hardware. For example, Interstellar add hardware flexibility to support different loop tiling or ordering. Flexible start to add hardware flexibility to support different compute order. And for example, Iris V2 also start to add hardware flexibility to support spatially partition across different dimensions. Yeah, so there are a lot of different DNN accelerators adding flexibility in different manner. However, there are lack of formalism. How do we measure this kind of flexibility? So it's hard to evaluate the benefit and trade-off across different DNN accelerators, which makes it challenging to extract the learning from different proposals and propel the next accelerator design. As you may notice, the flexibility here has some implication of the diversity of the mapping they can support. So in this work, we define flexibility as the hardware and software support for running diverse mapping for the same workload. However, why supporting diverse mapping is so important? Because different mapping lead to drastically different latency, energy, power, area, performance. As you can see from the result of time loop and gamma, there are up to 2 orders of magnitude difference of different mapping in the same workload. So what actually forms a mapping? In this work, we focus on interlayer mapping, where interlayer mapping like fusion is not considered. For example, to express the mapping of a convolution 2D, first we have a tiling axis. First, it is not likely we can fit the whole tensor on the on-chip buffer. Therefore, we'll use tiling to move partial of the tensor on-chip. The tile size decision will dictate how efficient we utilize the buffer and compute. Second, we have order. The order we fetch and execute the tile is also important because it will dictate which dimension we utilize the most. For example, they are weight stationary, essentially keeping the weight at the outer loop and reusing the weight. Third, we can choose to parallelize the compute across PE. Which dimension to parallelize can dictate the PE utilization. Lastly, logical mapping shape, or called level of tiling. It describes the number of tiling levels we use in this mapping. It could correspond to the buffer hierarchy, such as L1, L2, L3, and main memory. It also describes the logical shape of the compute unit, like the 2D P array of 16 cross 64. Therefore, T for tile, O for ordering, P for parallelism, S for shape, forms the full mapping axis for DNN accelerator. Here we have a two example of tiling. For the simplicity, we assume gen workload and the focus for PE array. Here, A represents input, B represents weight. We assume weight stationary, meaning we prefetch the weight and stream in the input. Now let's see what could be different tiling option. In option 1, you tile A into 2 smaller tiles. In option 2, you tile B into 2 smaller tiles. Let's see what's the performance implication. In option 1, the first half of B tile is prefetched and A tile 1 is streaming. Then we fetch the second half of B tile and streaming A tile 1 again. And we repeat the same process for A tile 2. To summarize, PE utilization is about 100%, and both A and B are read from memory twice. Option 2, B tile 1 is fetched and the entire A tile streaming. Then we fetch B tile 2 and streaming A again. The utilization is about 100%. However, we now only need to read B once. Let's see another example for order. In option 1, it could be, as we used in the previous slide, like weight stationary. Then A will be read and streaming twice. In option 2, we can change it to input stationary. Then A is fetched and B streaming. Then both A and B are read only once. For parallelism, in option 1, we can parallelize across these two dimensions, and the P utilization is about 50%. And if we change it to parallelism dimension to another 2 dimensions, then P utilization could be 100% utilized. For logical mapping shape, in option 1, A is read and streaming twice. Then P utilization is 50%. In option 2, if we can support a more flexible logical mapping shape, which is also 2-level tiling in our example, we fetch the second half of B to the lower half of P array. Then we could read A only once and multicast, and P is 100% utilized. However, flexibility is not free, so there are some costs of the flexibility component. For example, for tiling, one practical consideration is using hard partition, input weight, output buffer, or the soft partition one. Apparently, soft partition will have more flexibility, but also has higher complexity. Second, ordering. It will introduce configurable address generator to dictate order of buffer fetching. For parallelism, we need mux and some control logic alongside PE to control spatial or temporal reduction. For shape, we need network on chip to support different ways of PE clustering. So these flexibility are not free. Therefore, how to cleverly support them is an important question. In this talk, we discuss 2 aspects. First, which axis is more critical to support than the other? And second, along each axis, do we fully support them or partially support them to save some area and power costs? So we have discussed there are 4 mapping axes, T, tiling, ordering, parallelism, and shape. And to support or not support them, will form a 16 different class of accelerator. For example, class 000 means no flexibility, and class 111 here means all the TOPS flexibility axes are supported. Different accelerator pick to support different combination of mapping axes because they have different design budget and also targeting different workload. Next, along each axis, we can also choose to fully support them, partially support them, or make it inflexible just to stick to one fixed mapping. So the flexibility degree can go from 0 to 1. And we call this degree fraction. It means fraction of the supported map space. For example, to describe a tile flexible accelerator on ResNet workload, we could say like this. It is a T-flex accelerator with 0.8 fraction on ResNet workload. It means hardware has flexibility to support 80% of the tile size combination of ResNet workload. So formally, fraction is defined as is the supported map space over the entire map space. Here we show an example of the entire map space of a layer in ResNet. Here, the darker red means higher performance point. We can observe that there are multiple high performance regions which we circle in green. Now let's assume here we have a hardware with 0.5 fraction. Then what it means could be like this. The yellow part is supported 50% of the map space. Potentially, the supported map space might not be large enough to cover some of the high performance region. Larger fraction has higher chance to cover higher performance region. So the performance of the supported region actually depends on workload. However, the extreme case could be fully flexible. Then we are always sure we can cover the best possible performance point. So increasing fraction could make the hardware to be more future-proofing. It means it can cope with more diversity in the model. Let's see some evaluation. Here, the table is the hardware resource configuration of the modeling accelerator. We perform two sets of case study. First is the study of fully and partially flexible, and we evaluate using amortized workload along each of the four mapping axes. In the case study set 2, we want to show how the flexibility can benefit the accelerator to cope with more diverse model. We show a what-if situation. What if we added more flexibility into an Alexnet accelerator 8 years ago? How would it perform for the new DNN workload nowadays? In terms of new DNN workload, we consider ResNet, MobileNet, and MNASNet, essentially more REST and convolution-based model, and both DRIM and NCF, which are mostly composed of fully connected layer. First of all, let me describe how we consider partially flexible in this case study. It means it supported some few selected combination of the mapping. In the partially tiled flexible accelerator, we consider equally hard partition input weight and output buffer. For order, we only allow one type of order in each input weight and output stationary category. For parallelism, we only allow channel parallelism or activation parallelism. For shape, we only allow the PE array to be logically partitioned with a coarse granularity of 16 cross 16. As you may see in this table, you can see that tile flexibility is most impactful. It can improve the performance from inflexible to fully flexible the most. So tile is the most impactful axis. And also from this order axis and shape axis, you can observe that the orange bar, the partially flexible one, is very close to the green bar, the fully flexible one. It is because the partially flexible on order and shape can give compatible performance to fully flexible one. In the second case study, we want to show how flexibility can help future proving. We have two accelerator configuration. Alexnet accelerator means an accelerator specialized for accelerator specialized for Alexnet, and X model accelerator means an accelerator specialized for X model. Here we show their normalized latency to run the DNN model, the lower the better. For example, the blue bar here in MNASNet means I take the exact Alexnet accelerator and directly run MNASNet on it without any tuning. What is the performance? And the orange bar here means what if I completely redesign the accelerator to tailor for MNASNet? What is the best possible performance? Apparently, the specialized accelerator, the orange bar, can achieve better performance than directly using Alexnet accelerator, the blue bar. Next, if we group the model by convolution and fully connected, we could see a clear trend of performance difference between convolution and fully connected model. Alexnet accelerator as an accelerator originally tailored for a convolution model can perform relatively well across another convolution model as well. It is because there are some general mapping idea that is actually transferable between convolution to convolution model. For example, the Parisian dimension choices or stationary choices. And we'll come back to this later. Now let's start to add flexibility into the Alexnet accelerator. For example, Alexnet T-flex means what if we add tile flexibility into the accelerator when we are designing Alexnet accelerator back in 2014. First of all, given the buffer sizes, number of processing elements, these are the area codes of each flexibility axis. One thing we can notice is that the additional area cost is not that affordable if we amortize to the cost of the entire accelerator. Then in the graph, we can see that the orange bar here is always the lowest in the convolution model. It means adding tile flexibility can improve the performance the most. However, we can observe adding tile flexibility to DRM and NCF is not really helpful. It is because the performance is bottlenecked by suboptimal choices along other mapping axes like parallelism and shape. However, BERT can benefit from the tiling. The key difference is that language model usually has higher dimension tensor and has more chance to leverage the parallelism and strategy tailored for convolution. And we can see that parallelism and order flexibility is pretty helpful for DRI and NCF. It is because these models are so different from convolution model. To have flexibility to make different parallelism and order choices is essential. Therefore, parallelism and shape flexibility are impactful to be future-proof to new workloads. Next, let's add more flexibility into the Alexnet Accelerator. We do this experiment in a sensitive analysis way, where we enable 3 out of 4 mapping assets to see how critical each mapping asset is. For example, Alexnet no T-flex means Alexnet without all mapping assets, with all mapping assets except tile. First of all, we show a baseline, which is the green bar. The green bar means all the mapping assets are enabled, which is the most flexible and will be the most powerful one. We can observe that the orange bar and the yellow bar are the highest for one and another model. It means that the accelerator is more sensitive to tile and parallelism mapping axis. We can observe gray bar is almost as low as the green bar across all models. It means older is less sensitive. And to explain it in another manner is that proper combination of T, P, and S mapping assets can mostly compensate the lack of older flexibility. Therefore, partially flexible accelerator can sometimes be competitive with fully flexible accelerator. Here are some takeaways. The additional area cost of flexibility is not as substantial when amortized to the cost of the entire accelerator. Tile flexibility is the most critical. Parallelism and shape flexibility are important to be future-proof to unknown new workload. Proper combination of tiling, parallelism, and shape flexibility can overcompensate the lack of older flexibility. Partially flexible accelerator with lower area cost can often achieve competitive performance to fully flexible one. Conclusion. Flexibility of hardware is often discussed in a vague manner. We define flexion to represent the flexibility of DNN accelerator. Flexion indicates the fraction of supporting map space to the entire map space. Flexion enables us to study DNN flexibility, impact, and trade-off in a systematic manner. And we believe this will help both compiler developer and architect to systematically develop flexibility-aware accelerator design. Thank you.